All right, today we are cracking the code on an absolute classic, the two-sum problem. Now, you will see this question pop up in tons of tech interviews, and there's a really good reason for it. It is the perfect gateway to understanding how one little shift in your thinking can lead to a solution that is worlds better. So let's just dive right in. So let's start with something we can all relate to. Picture this. You're at the checkout and you've got a gift card for exactly $9. You want to use the whole thing, no cents left over. So you need to find two items in your cart that add up to precisely $9. Now, if your cart is overflowing, how would you do that without having to pair up every single item with every other item? That little puzzle, well, that's the core idea of the two-sum problem. Okay, let's translate that shopping trip into the language of code. The formal problem statement goes like this. We're given a list of numbers, an array that we'll just call nums. We're also given a specific goal, a target number. Our job isn't just to find the two numbers that add up to that target, but to find their positions in the list, or what we call their indices. Let's make this super clear with an example. Okay, so our input list is 2, 7, 11, 15, and our target is 9. Right away, you can probably spot that 2 plus 7 equals 9. But remember, the answer isn't 2 and 7. It's their positions. In programming, we start counting from 0. So the number 2 is at index 0, and the number 7 is at index 1. So the correct output is a list containing 0, 1. So where do you even start with a problem like this? Well, the most straightforward, intuitive way to think about it is what we call the brute force approach. And yeah, it's pretty much exactly what it sounds like. We're just going to muscle our way through it and try every single combination until something works. The logic here is really simple. You just grab the first number, which is 2 in our case, and you start adding it to every other number in that list one by one. So you check, is 2 plus 7 our answer? Is 2 plus 11 our answer? What about 2 plus 15? In this specific case, we actually get lucky. The very first pair we try, 2 plus 7, adds up to 9. So great, we're done. We can return their indices and call it a day. But, and this is a big but, here's the problem. This approach is really slow. In computer science, we have a way to measure this called big O notation. The brute force method is what we call O(n squared, or O of n squared. All that means is for every item in our list, we have to loop through the whole list again. So as the list gets bigger, the number of checks we have to do just explodes. This is definitely not a solution that scales. I mean, just think about it for a second. If your list had 100 numbers, you'd be doing roughly 10,000 checks. What if it had 10,000 numbers? You're looking at around 100 million checks. That's just way too slow. So this forces us to ask a much better question, a question every engineer has to ask. Can we do this smarter? Is there a way to solve this by looking at each number just one time? And the answer to that is a huge, resounding yes. There is a much better way. The secret, the key to unlocking this, is to give our algorithm a memory. What if instead of checking the same numbers over and over, we could just remember what numbers we've already seen and where we saw them? This simple little idea, it's a total game changer. The perfect tool for this job is something called a hash map. You might also hear it called a dictionary in some languages. The easiest way to think of it is like a super fast digital address book. It stores information in pairs, a key and a value. For us, the key will be a number from our list, and the value will be its index. And the real magic of a hash map is its incredible speed. You can ask it, hey, have you ever seen this key before? And you get an answer back almost instantly. Okay, enough with the theory. Let's see how this actually works. We're going to go back to our example and build our elegant one-pass solution step by step. So let's walk through the logic. We start at the very first number, which is 2. The first thing we do is ask ourselves a question. If our target is 9 and our current number is 2, what's the other number we need? Well, 9 minus 2 is 7. So we're looking for 7. Now we check our memory, our hash map, and we ask, have we seen a 7 yet? The map is totally empty right now, so the answer is no. Okay, no problem. We just take our current number, 2, and its index, 0, and we add it to our map for later. And now, here's the aha moment. We move to the next number in the list, which is 7. We ask the same question, what number do we need? The target is 9, our number is 7, so we need a 2. Now we check our map again. Hey map, have you seen a 2 before? And this time, bingo. The map instantly says, yes, I have. And I saw it at index 0. We found our pair. We have the index from the map, which is 0, and our current index, which is 1. We're done. And just like that, you can see the sheer power of this approach. By using a little bit of memory, we solve the entire problem by going through the list just once. This gives us a time complexity of O of n. That means if our list had 10,000 items, we do about 10,000 operations, not 100 million. It is a staggering, massive improvement. Now, a truly great solution has to be robust. It has to handle all the tricky little possibilities. Thankfully, the problem statement gives us a few guarantees, like telling us a solution will always exist. But our hash map approach is strong enough to handle things like duplicate numbers, like 3, 3, or even negative numbers, without needing any changes to the logic. That's the sign of a really well-designed algorithm. So we have made this huge leap forward in performance. We went from a really slow solution to a blazing fast one. But in the world of programming, you have to remember, there's rarely such a thing as a free lunch. To get this speed, we had to make a classic trade-off. Here's the deal, plain and simple. We traded space for time. The brute force method was incredibly slow, O of n squared, but it used almost no extra memory. We call that O of 1, or constant space. Our new hash map solution is incredibly fast, O of n, but it has to use extra memory to store that map of numbers we've seen. In the worst case, we might store every single number from the list, which gives it a space complexity of O of n. And that right there is the central lesson of the two-sum problem. It's not just about finding an answer. It's about understanding this fundamental concept. This principle of trading memory to save on time is an absolute cornerstone of writing efficient code. By teaching our algorithm how to remember what it's already done, we save it from having to do all that work over and over and over again. So as you move forward and tackle more complex problems, this is the question you should always be asking yourself. For this specific application, what is my most precious resource? Is it raw speed? Or is it keeping memory usage to a minimum? Understanding how to navigate that trade-off, well, that's what separates a good programmer from a truly great one. Thanks so much for tuning in.